They're open to belittling other people besides me. I like it. It's good. It's good. You know, that's right. As long as you're a jerk, if you're a jerk to everyone, it's okay, right? If it's localized to just one person, that's when it's unfriendly. All right? I'm just saying. I'm not talking about the back row right now, of course. But I will begin. Heavenly Father, we thank you for this day. I thank you for the students. And I just pray that you'd guide our work today. Help us to glorify you, Lord, and what we do, Lord. In your name I pray. Amen. All right, so systems of differential equations. Let's get into it. We have seen that eigenvectors do many, many things, right? If we can, let me just recap the method. Let's recap the method. The method is, first of all, to understand how to write the system as a matrix problem, right? So you're given the system of differential equations, ordinary differential equations. Step number one, right, is to identify, a vector of variables and your matrix such that given system becomes dr dt equals to AR, right? Later, we'll add another chapter to the story. Eventually, we'll look at the non-homogeneous problem. Later, we'll add this later, okay? Maybe today. Hopefully at the end of today, I'll show you how to deal with a non-homogeneous problem. Once we understand the homogeneous problem, the non-homogeneous problem is pretty straightforward. I'll come back to that. Step number one is to identify the matrix of the system, all right? Step number two is we calculate the determinant of a minus lambda I equals to 0, right? This is an nth order polynomial equation, which means that the fundamental theorem of algebra says that there exist, what? N solutions, possibly complex, possibly repeated, so it can be solved. Now, the actual process of solving it for a given problem can be complicated, right? But we find the solutions to this, and those are called what? Yeah, the solutions are called eigenvalues. Or some people will call them characteristic values. All right. Then step 3 is you find solutions to a minus lambda I u equals to 0. All right? And I should emphasize here, put it in red, this is important, non-zero solutions, right? What are these non-zero solutions called? Eigenvectors, right? So these are eigenvectors. This gives us an eigenvector with eigenvalue lambda. All right? All right. Now, 4, count your blessings. Name them one by one. Let's see here. So, like, you got yourself a U1, you got yourself a U2, UK. All right. You collect a set of eigenvectors. So these are linearly independent eigenvectors. And let's suppose that they have eigenvalues lambda 1, lambda 2, lambda k respective, right? As we learned, some of these could be complex, right? If there's a complex lambda in the midst, then the eigenvalue has a conjugate pair, lambda, what do we use, stars or bars? What's the complex conjugate of lambda? Did I do lambda bar in here? Did I do star? I know I did bar in abstract. What did I do in here? I did star in here. Goodness gracious. So depending on what book you look at or what course you're in with me, lambda star or lambda bar, I mean to be the complex conjugate of lambda. All right. So sorry about that. If you're in both of these courses, it's I've done worse. Stars or bars. But anyway, complex conjugate. They have to come in conjugate pairs because the matrix A is real, which means that the characteristic equation's a real polynomial equation. And real polynomial equations have complex zeros which must come in conjugate pairs. This is just algebra. All right. So, all right, fine. Count your blessings. And then let's suppose that these are all real. Suppose that these are real. Maybe you've got some complex ones, right? So we could also have like A1 plus IB1 AM plus IBM. Here the A's and the B's are reals corresponding to alpha 1 plus I beta 1, alpha M plus I beta M. So here I have K real, here I have M complex. So if you count, what's the total number of solutions that I'm sketching so far? K real solutions, right? And the M complex solutions, remember we take the real and imaginary parts of those, and they give us real solutions. Let me review that briefly. If we have Z equals to e to the lambda t times u, where lambda is alpha plus I beta, and u is equal to a plus ib. In other words, the real part of lambda is alpha, the imaginary part of lambda is beta, the real part of the vector u is a, the imaginary part of the vector u is b. Okay, that's the language here. We're assuming that b is not equal to 0, right? If u is an eigenvector, the theory of linear algebra, and it's not that hard to prove, but you can prove that if u is a complex eigenvector, that the real and imaginary parts are actually linearly independent. Right? So like the a and the b vector, they're both non-zero, and they're independent. That can be shown. That's a consequence of u being an eigenvector, complex eigenvector with eigenvalue alpha plus I beta. Again, assuming beta is non-zero. And the cool thing, of course, then is that this z we can break up into a couple of real solutions, and here's how that goes. This is e to the alpha t times cosine beta t plus. So at the end of this, we're going to find a formula that you guys can just use for problems where we have a complex eigenvector, okay? Like, I don't think that you need to actually go through this calculation every time we do this, but I'd like you to use the formula with understanding, which is why I'm deriving it right now, okay? So multiply that out, which we got? We've got e to the alpha t cosine beta t times the a vector. And see, I times I is what? It's I squared, which is minus 1. So I get minus the sine of beta t times the b vector plus I e to the alpha t. Then I've got myself a sine beta t times the A vector plus a cosine beta t times the B vector. The difference between what I wrote in the first set of parentheses versus the second parentheses is the first set of parentheses, that minus is coming from the fact that I squared is minus 1, right? Everywhere else, we just have product of positive things, which gives us positive. Now, having done all this work, you can identify straight up that this is the real part of the complex solution z, and this is the imaginary part of the complex solution z, right? But, you know, let me just take a moment of our time to think about this. If we have dz dt is equal to az, what's that mean? That means that d dt of the real part of z plus I times the imaginary part of z is equal to a times the real part of z plus I times the imaginary part of z. But what does that say? How do we differentiate this? Well, this gives us that d dt of the real part of z plus I times d dt of the imaginary part of z is equal to a times the real part of z plus I, a times the imaginary part of z. So what I'm looking at there is a complex vector equation. A complex vector equation has two real vector equations inside it. In particular, we have that the real part matches the real part. Right? What is the real part equaling the real part I underlined in pink just now? Tell us. What's that say about the real part of z? It's a what? It's an eigenvector. Yeah, it's a solution. Right, right. It is a solution, is the thing I was fishing for. And what about the imaginary part? If we just focus on, ignore the I, equate the imaginary part to the imaginary part, like this and that, right? We have that the imaginary part is also a solution. So the real and the imaginary parts of a complex solution are separately real solutions to the given problem. Right? Every time we find a complex solution, we find a pair of real solutions. And not just that, I've written the formulas for those on the board, right? What's the formula for the real solutions? This is like the first one, right? This guy. You could say that as x1. Oh, I'm sorry, r1 in my current lingo. And no I in it, all right? The second real solution is over here, r2. So every, every complex eigenvalue and complex eigenvector gives me a pair of real solutions in this fashion. Does that make sense? I mean, I actually did one with numbers last time, or at least we looked at it on the projector, right? And I think if we had to summarize last class, never before has a lecture so eloquent been given, right? Like the words that escaped my mouth, they were magnificent and smooth and flowing. No mistake was made. I mean, right? Just to be clear for those who couldn't hear it for themselves, it's really, really good. What's that? Well, we don't need proof. I mean, you can tell from what was written on the board, it was really great. Like, yes, half the lecture was scrolling through the PowerPoint. That is true. But I hope that was useful. I thought I heard something. It sounded like bad algebra. I feel like Dr. Sprano's nearby. Usually when I hear somebody shouting in another room, it's Dr. Sprano shouting at students for their bad algebra. They deserve it. I've seen what they do. Some of you may even be included in that number. I don't know. But I don't shout. I just take off points. Anyway, we've counted our blessings. And so counting the blessings, how many blessings are there? There are k plus 2m solutions here, right? If this is less than n, then that means that something's missing. right? In other words, if after you look for all of these eigensolutions, complex or real, and you tilt your head and squint and go, wait a minute, I don't have as many solutions as the system is large, right? If it's a system of n differential equations and I only find like n minus 2 solutions, something's missing, right? So what are we missing in the current, with this current technology? Like, where is the rest of the solution set coming from? And the answer is something called the matrix exponential. So let's look at that. So the matrix exponential is what it sounds like. It is, here's the definition, e to the b is equal to I plus b plus 1/2 b squared plus 1 over 3 factorial b cubed plus dot 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 dot. In other words, you've got the sum n equals 0 to infinity of b to the power n divided by n factorial. You may recognize the series I just wrote as being the series for the exponential function. So this is a natural definition for the matrix exponential. There are other definitions, but this one will serve us well. So you can tell me some things already, like what's e to the 0 going to be equal to? If I take e to the 0 matrix, what do we get? Let's try again. What's e to the 0? What's that? 1? Well, almost. It's this thing. It's I. So that I is the diagonal matrix that's got 1s on the diagonal, which you could also write like this: 1, 1, that 1, right? If you like, we can put a little sub n on this to emphasize it's the n by n identity matrix, right? But this matrix serves as the number 1. The key thing about the identity matrix is what? Is that if we have in times any matrix x, we just get x again. And if we have any matrix m times the identity matrix, we just get the matrix again. I mean, the identity matrix, it's like it was never there, all right? Okay. That's my first observation. E to the 0 is equal to I. All right. What else can we say about this matrix exponential? Well, some more fancy math stuff for you. If we, you're like, well, I remember calculus 2. I lost a lot of points over convergence and divergence. And I lost like 2 weeks of my life to some professor blathering on about what it means for things to converge. And this seems unfair. You've just added a bunch of matrices without even so much as discussing what it means for a sum of matrices to converge, right? Well, none of you complained, actually, but you might. And there is a well-defined meaning for the convergence of series of matrices. The idea is simply this: the size of a matrix, the norm of a matrix, if you will, the absolute value, generalization, it's just going to be the square root of like b11 squared plus b12 squared plus plus bnn squared. In other words, so here's a particular one. If I wanted to calculate the length of the matrix 1, 2, 3, 4, the length of the matrix 1, 2, 3, 4, the standard definition would be square root of 1 squared plus 2 squared plus 3 squared plus 4 squared. So it's to calculate the length of a matrix, you just think of it like a long vector where you've just strung out the components, and that's the length of the matrix, right? It turns out that there's like a super slick formula for this. This is actually the trace of b transpose b as it happens, the square root of that. So there's like a super cool formula for it, and you can prove a bunch of stuff about it. But long story short, with respect to that notion of distance, we can prove that that series converges, generalizing the notion of convergence from calculus 2 in this straightforward way. it can be shown that that series, in fact, converges for any matrix B. Okay, so this is like known analysis. We don't have to prove it in here. I could put it in your quiz if you'd like. We have some math majors in here. It'd be good for you, right? No? No, checking. All right, well, that unpleasantness aside, let's get back to more things about this. So one of the key features of the matrix exponential is that if we have AB is equal to BA, then you can show that e to the a times e to the b is equal to e to the a plus b. All right. This is an identity that you can prove. Here, I'll start doing that for you. How about it? E to the a times e to the b is what? I plus a plus 1/2 a squared plus dot dot dot. And here we've got I plus B plus 1/2 B squared plus dot dot dot. So let's multiply that out. I times I is I times B is B. Then we got 1/2 B squared. So what I did so far was I just did I times that. I distributed, all right? And I'm only going to keep the quadratic order, all right? Just keep the quadratic order. Next up, A plus AB, and then, well, then I would have A times 1/2, I would have 1/2 AB squared, but that's third order, so I'm going to not even pay attention to that. I'm only keeping to terms that have at most two matrices, okay? So the next thing doesn't matter. And then I get a 1/2 A squared, and I believe that's it to second order. It's just that. And so if you look at this, what we have is I plus A plus B plus 1/2. And then here's where you got to be careful. The main thing about if matrices commute, then so what would, if we have two matrices A and B and we multiply them, if we square A plus B with A plus B, like multiply A plus B times itself, forget for a second that they commute. If they don't commute, or even if they do, we first get this, A squared plus AB plus BA plus B squared. So in order to rewrite this as, A squared plus 2AB plus B squared, we need what? We need that AB is equal to BA. And when you study matrix multiplication, one of the things that, and I will let you discover this on the quiz at least, I'll have a problem where you see this, since a lot of us are still learning how to multiply matrices, right? Matrix multiplication is not commutative. There's lots of matrices that if you multiply them one way and multiply them the other way, you get different answers, right? So this is not, not for nothing. This is an actual condition on A and B that they commute. That's special. But that being said, I can look at this 1/2 A squared plus 2AB plus B squared. And the thing is, this is actually just, right, it's already on the board here. This is A plus B squared, right? So A plus B squared is equal to A squared plus 2AB plus B squared when A and B commute. More generally, A plus B squared is this thing up here, all right? Because we can't change BA to AB. But anyway, there it is. We have up the quadratic order A plus B plus 1/2 A plus B quantity squared plus dot dot dot. A lot of times I assign this as a homework in here, but I think it's productive for us to go through it together today. And what is that? Well, that's the matrix exponential to the A plus B power. So there you go. That's a short, up to second order proof at least, that e to the A times e to the B is e to the A plus B in the case that A and B commute. the full proof for math majors would involve, I would say, first of all, proving the binomial theorem for matrices A and B which commute, then using the binomial theorem in conjunction with the Cauchy product to prove that, in fact, we get this identity for the function defined by the exponential series. This is currently a problem, give or take, in my complex analysis course. So, not with matrices, but it's the same song and dance. All right, now that we have this, question. Does A and minus A commute? Does a matrix commute with its negative? Like, think about this. If I have A times minus A, is that equal to minus A times A? Well, the answer is yes. We can pull minuses out, and so both of these are just equal to minus A squared. So any matrix commutes with its negative. What that means then is we can look at e to the 0, which is e to the A minus A, right? And we can think of, A equals to A, and B equals to minus A. What do we get? We get e to the A times e to the minus A. But what is e to the 0? It's the identity. It's 1. And so what this equation right here is, this is showing us that e to the A, the multiplicative inverse of it, is equal to e to the minus A. In other words, what we've shown is that the matrix exponential for any matrix is invertible. The matrix exponential is an invertible matrix. The matrix exponential is an invertible matrix. In other words, if we were to calculate the determinant of e to the b, we would get that it's not equal to 0. By the way, let me just tell you some things that, without proof, if you will. These things we could prove in linear algebra, and I think they're edifying for you to know about. So let me just mention them. One of the things I would mention, so let me just put this in the category of fun facts. So some fun facts for you. First of all, the determinant of the exponential of a matrix is in fact given by the ordinary exponential of the trace of that matrix. If you didn't know, the trace of a matrix So, we have an n by n matrix. The trace is defined to be the sum of the diagonals. So it's like b11 plus b22 plus da 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 plus bnn. For example, the trace of the identity matrix is just equal to 1 plus 1 plus 1 plus 1 n-fold times. So like the trace of the identity matrix is just n, for example. But this is an identity which is known. The determinant of the exponential is the exponential of the trace. With this formula in hand, it's really easy to understand why we already found the determinant was non-zero, right? How about an exponential? Can an exponential be 0? No, right? Be it real or complex. In this case, it's a real exponential. Another thing I'll mention for you, because it's near and dear to my heart, is that e to the a times e to the b is in fact given by e to the a plus b plus 1/2 the commutator of a and b, and then plus or minus 1/12 a with ab, plus or minus 1/12, I forget which is plus or which is minus, b times b comma a, plus da da da. And this is a a series rather, of nested commutators. This thing I'm writing down is the so-called Baker-Campbell-Hausdorff relation, BCH relation. And it says that if you want to multiply two matrix exponentials, if you know how the commutator works out for the two matrices in the higher commutators, you can multiply the matrix exponentials according to those rules. Yes? A commutator is a good question. A commutator is 0 if the matrices commute. So like AB is AB minus BA. So that's all that means. We ran across this once a little bit earlier in the course when I was talking about the fact that smooth operators don't commute. Right? I mentioned that the commutator shows up in quantum mechanics. Two physical observables are simultaneously observable with infinite precision. If their commutator is 0, they can have eigenstates which are simultaneous eigenstates to the Hamiltonian, the energy operator. If the commutator is non-zero, then you can't measure them both simultaneously. There's some uncertainty. Anyway, you can study that more in your quantum mechanics course. But anyway, so you see what happens to this infinite series is when A and B commute, these are all gone. Right? But on the flip side of things, if you know how to calculate this AB minus BA, if you know specific formulas for those, you can use those formulas to multiply the matrix exponentials. Right? This technology lies at the heart of modern physics. This is A and B lie in what's called the Lie algebra of the problem, whereas e to the A and e to the B lie in what's called the Lie group of the problem. And matrix Lie groups are used to form fundamental physics these days, right? Fundamental particles physics, high energy particle physics, all built over matrix groups of these sorts of things, actually. Now, this is like arithmetic for those people. It's not like they do much worse things in terms of infinite. Anyway, let's not get into all that, Feynman diagrams and harder things. But this is at the start of it, is this kind of fun with matrices. Now, at this point, you should wonder, great, you've got this matrix. You can calculate the matrix exponential from any matrix, right? Well, what does that have to do with solving differential equations, right? So let's think about that. Let's see here. So what I'm going to do now is I'm going to consider the formula e to the TA, right? And since this is a matrix of functions, let's call this thing equal to x, right? What's dx dt? ddt of what? E to the TA, which is, all right, great. I'm just, nothing happened yet. What is that, though? We've got I plus TA plus 1/2 t squared a squared 1 over 3 factorial t cubed a cubed, right? What happens when you differentiate that? What's the derivative of a constant matrix? 0, yeah. And what's the derivative of TA? Yeah. What's the derivative of 1/2 t squared a squared? So the way this works is we just differentiate the coefficient, right? And the a squared just factors out because it's constant. All right, that's the differentiation here. If you guys didn't follow me already, now you told me just a second ago. What was the second term there? What did I have? What's this work out to? But I've got the 1/2 as well, right? So,
yeah, just TA squared.
TA squared. Okay, so a plus TA squared. What happens with the next term up? 3 factorial. What's the derivative of? I mean, generically speaking, if you look at the derivative with respect to time of 1 over k factorial, t to the k, what do we get? We get k times t to the k minus 1 over k factorial, right? Which is what? T to the k minus 1 over k minus 1 factorial, right? Because the k and the k factorial reduced to just k minus 1 factorial. And so it's no surprise that this becomes what? 1/2, right? 1/2 t squared a cubed. The next term would be 1 over 3 factorial t cubed a to the 4th, right? And so forth. Now, if you look at that, it's almost the matrix exponential again, except we've got an extra copy of a. So we can either factor a out to the left, or we could factor a out to the right. I suggest that we factor a out to the left so that we can make the step that's not written down yet. But let's factor a out to the left. That gives me I plus ta plus 1/2 t squared a squared. And what is this? Yeah, I mean, what is this? What's that? It's the matrix exponential. It's exactly this again, right? Because e to the ta is defined to be I plus ta plus 1/2 ta squared plus 1 over 3 factorial parentheses ta cubed, which is that. So we've got, yeah, a e to the ta again. And if I go back to my x notation, this is ax. Now I use the big X because I used it another day when I was talking about a what. What did we learn? If we took n solutions to the differential equation and we glue them together in a matrix, we get a solution matrix. And that's if and only if, right? If the solution matrix satisfies the equation dx dt equals to ax, that means that every column in that matrix is itself a solution to the given problem. What have we just shown? We have shown it was not a bad algebra. That was just a, hey. That could have been like, would that be some, I mean, would he react that way to somebody having their phone out? I mean, I don't know. Yeah? Okay. Anybody got their phone out? Anybody clandestinely texting in your lap right now? No, I don't see any. I usually don't. For me to care, it has to be this sort of the following context, like, wow. So I was doing an independent study of differential equations once upon a time in the summer. I had 3 students in the room. It's now dirt or grass out there, all right? This is the old science hall or applied science. 3 students in the room, right? And the one guy is sitting there 10 feet from me in this kind of desk with his phone in his lap. Like, what are you doing? Like, and if he'd been doing perfectly well, it would have been fine, but he was not. Oh well. I tried to tell him, do not take organic chemistry and differential equations in the summer. I was like, you could do this, but not trying to also take organic 1 and 2. Did not listen to me. And so he just had to take organic 1 and 2 again. What do you know? And the A he had in differential equations became a B. So, oh well. Anyway, that's in the past. All right, so I now have enough common sense to not do independent studies of differential equations in the summer, right? If you guys want to do that, well, it's too late for you, but anyway. Okay, so we have that the matrix exponential is a solution matrix, and what does that mean? Is it a fundamental solution matrix? What was a fundamental solution matrix? It was a matrix which is invertible, right? Which has linearly independent columns, if you know enough linear algebra. The matrix exponential is just such a thing. We've just proved its determinant's non-zero. wait a minute. So you mean to tell me that the matrix exponential has n columns, which are, each one of them is a solution, and they're linearly independent. Doesn't that just solve the problem entirely? In fact, it does. I can tell you the solution, and this won't get you won't get you much in terms of. I mean, we're engaged in the process of dissecting this solution. All right. So like this is, I mean, this is not wrong what I'm about to write, but you know, I'll be like, well, that's good. I'm glad that you heard me when I said that, but we need to unravel it. Okay. But there you go. I mean, this is the general solution to dr dt equals to AR. That is the solution. For which matrix? For what choice of A? That's the thing, is there's no restrictions on the calculation we just did. A just has to be a constant matrix, and then that's the solution. This solves any system of n-order differential equations with constant coefficients. To me, that's a frighteningly general solution. I mean, that's to me, it's shocking that that's possible to do it so nicely. But that's great. What are the actual details of that, right? What's the formula, the scalar solutions, given that boxed formula? Like, how do you unravel that? What is it? It's an infinite series of matrices, right? So the devil's in the details here. How do you actually unravel that formula and produce real formulas? Well, that is where the next chapter in the story comes into play, which is generalized eigenvectors. So now that we have a solution, we have to figure out how to unravel it and take apart the pieces and use those pieces to complete the missing pieces over here to finish the story. So how to unravel e to the ta. The ultimate answer is eigenvectors and generalized eigenvectors. Let's start with eigenvectors, since we're already somewhat uncomfortable with those. So, that was a joke. All right, so we have a minus lambda I times u equals to 0 for an eigenvector, bless you, with eigenvalue 0, eigenvalue 0, listen to me, eigenvalue lambda. What is this? And as we discussed, this is equivalent to saying what? A u equals to lambda u, right? What would happen if we take e to the ta and we hit it with an eigenvector? What happens to this? Let's look at it at the I'll do a plus dot dot calculation because I think you guys will follow that fairly well. 1/2 t squared a squared. So what happens when we multiply this series of matrices by an eigenvector? To start with, we get iu, right? Plus t au plus 1/2 t squared a, and that's a au. So you guys tell me though, what does the AU simplify to? That simplifies by definition of eigenvector to lambda u, right? This is lambda u. This is lambda u. So what we got? We've got, and IU is just u. So we've got u plus t lambda u plus 1/2 t squared lambda, and then there's still an a left there, AU. But what is AU again? What's that? Lambda u, yeah. So this is lambda u once more. Now we got two lambdas. We got t squared lambda squared u, right? And you can see you could keep doing this process for the higher order terms, right? Like when we look at a to the k acting on u, we're going to get lambda to the k times u after doing like k-fold applications of the definition of the eigenvector. It's clear that this pattern continues, and if you tilt your head and squint, you can see what you got is 1 plus t lambda plus 1/2 t squared lambda squared da, 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 times u. What is this? What's that? Power series of what? Power series of T lambda. Okay. What function of T lambda? E to the T lambda, right. This is the power series of e to the T lambda. And then there's times u. Hey, wait a minute. We have seen this before. So what we have just derived is if you hit the matrix exponential with an eigenvector, out pops our beloved eigenvector solution, or eigensolution as I have called it before in here. The eigensolution. Right? This is a blessing we already counted. Right? That was one of, that's actually, I mean, I didn't write it down here, but this solution, right, is e to the lambda tu. We looked at those last class, right? So great. You're like, okay, wonderful, so we can reproduce what we already had. Where's the new stuff? How do you get the new stuff, right? So, and then here's where I have to do something that is, well, you know, less obvious. At this point, I need to derive for you guys something which I refer to as the magic formula, because it's where the magic happens. And so here goes. So e to the ta. So what I'm going to do is I'm going to make a lambda appear, right? So this is like short of, what's that called? Like close-up magic, like the sleight of hand. The mathematical equivalent of that, add 0, right? So you have t, and I do a minus lambda I, and then I do plus t lambda I. All right, like so. I've just added 0. Now, this is a good move because any multiple of the identity matrix commutes with everything. Right? So T lambda I is a matrix which commutes with anything. Commutes with all matrices. Of the appropriate size, of course, but yeah. So that means I have that e to the, this simplifies to e to the t lambda I times e to the t times a minus lambda I. Like that. Fun fact, if you take the exponential of a diagonal matrix, so if I take the exponential of the matrix 1, 2, 3, the way it works, you end up getting e to the 1, e to the 2, e to the 3. That's actually how the exponential of a diagonal matrix works out. You can prove this. Now, applying that observation to this term, this just becomes e to the lambda t times the identity matrix. And so, and I can just erase the identity matrix. I don't even care about that. And this becomes I plus t times a minus lambda I plus 1/2 t squared times a minus lambda I quantity squared plus dot 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 dot. So what I just wrote, I lovingly refer to as the magic formula. So there you go. You're like, well, okay, great that you love this formula, but how does it help us? Well, it doesn't help us until we understand that we can calculate something called generalized eigenvectors. What are generalized eigenvectors? Generalized eigenvectors are non-zero vectors designed to truncate the above formula. That's my perspective in here. That is not the perspective I take in linear algebra, but that's the perspective I take here. That's their purpose, to make that formula truncate to just a few terms. So think about this. The first case of this is just eigenvectors, right? A minus lambda I u equal to 0 implies that A minus lambda I to whatever power acting on u is equal to 0 for k greater than or equal to 1, right? So therefore, e to the ta on u is just equal to e to the lambda t u by star. I mean, we derived it a rather different way over here, yeah? I mean, here, but look, you can recover what we just derived using the magic formula simply by, if you imagine letting an eigenvector, let this matrix multiply an eigenvector, we have e to the ta times eigenvector. On the right-hand side, what happens when an eigenvector gets hit by a minus lambda I squared? The eigenvector with eigenvalue lambda has that be 0. What happens when you hit an eigenvector on a minus lambda I times the eigenvector? By design, it's 0, right? The only term that survives is the I, which is why we got the eigensolution by multiplying by an eigenvector. All right? So, what if we could find a solution like this? What if we could find a minus lambda I squared, u2 equal to 0? What if we could find a solution to that? What would that say then? If we could find such a solution, that would say that a minus lambda I to the k acting on u is equal to 0 for what? For k greater than or equal to 2. Therefore, e to the ta times u2, what would that give us? It would give us e to the lambda t, all right, times, u2 plus, well, t times a minus lambda I times u2, right? Which, hey, that's a vast improvement on an infinite series of terms, right? It's just 2 terms. It's kind of a pain to calculate. But actually, we can do even better. Because what we can do is we can arrange the generalized, by the way, this makes u2 a generalized eigenvector of order 2, provided that it's not an eigenvector of order 1, which is an ordinary eigenvector. So there's a trick that we can do. We can arrange these in chains. Let me show you that. So to get this, instead, we have a thought. All right, here's our thought, is that if I was to solve a minus lambda I u2 equal to u1, if I could solve that matrix equation, then what would that say about u2? If I multiply the equation by a minus lambda I, what's a minus I times lambda, what's a minus lambda I times u1? I mean, assuming u1 is an eigenvector, that's 0, right? So, in other words, rather than just solving a minus lambda I squared times u2 equal to 0, if we trade that instead for solving the so-called chain condition, all right, namely that a minus lambda I u2 is equal to u1, this so-called chain equation, if we solve the chain equation for U2, that makes U2 a generalized eigenvector of order 2, which is going to give me this, but then what? Chain condition says, oh, hey, that's also serving the purpose of making this formula nicer. See, because the chain condition says, I'm going to make that be U1. And so we get e to the lambda t times U2 plus TU1. And there you go. That is the solution that we have not yet seen in here. That was the missing link, so to speak. Not that we believe in that sort of thing, but so here's the missing solution, which is produced, of course, by a generalized eigenvector of order 2. So the theorem is that, in fact, this continues, and so you can get a chain like this. You have UK and UK minus 1, U2, U1. Each time in this chain, I'm multiplying by a minus lambda I, a minus lambda I, a minus lambda I. And so in this case, we'd have, U1, U2. Well, if I start with U, oh, fine. I'm writing them from 1 to k, but the point here is that a minus lambda I, U1 equal to 0, a minus lambda I, U2 equals to U1, dot, 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 a minus lambda I, the kth one, equal to the k minus 1th one, right? If you have a chain of generalized eigenvectors like this makes the kth one a generalized eigenvector of order k. And if you were to take such a thing and hit it on the matrix exponential, what would happen? You get e to the lambda t. And when you work it out from the magic formula, of course we get uk for the first thing. And then what comes next? Think about, we hit uk times a minus lambda I, we get uk minus 1, right? So we get plus t times uk minus 1. What happens when, here I'll write, let me write some, I would love to write it here, but it doesn't seem like it's worthy of staying on the wall forever. So instead I will write the little scribble side calculation over here in a purple bubble. All right, so how about t squared over 2 a minus lambda I squared uk. What happens with that? We get t squared over 2 a minus lambda I, right, times uk minus 1 from the first copy of a minus lambda I. It wasn't you, Ian. It wasn't you. All right, fine. I've created enough awkwardness. I'll go on. Then this gives me what? A minus lambda I times uk minus 1 is assumed to be uk minus 2. That's the way this works, all right? A minus lambda I times any thing in the chain gives me the thing, right next, down the chain in my current picture. So we get plus t squared over 2, bless you, yes, uk minus 2, and so forth and so on, until finally we get t to the k over k factorial, and then eigenvector u1 at the end of that. So I wrote down the formula for k equals to 2 on the other